Yeah, hello everyone. I'm Kajol and I'm from FAU Erlangen, and I will present a continuous benchmarking pipeline for waLBerla framework, which runs on different hardware architecture. So since we have to make it quick, I will quickly describe the uh, basics. That continuous integration is a software development practice which basically identifies and detects software feature degradation before it goes into the production. But continuous benchmark, where users perform their work, benchmark their work frequently and on regular basis. So this practice basically identifies and prevents software performance degradation before it goes into the production. Most of the CFD softwares nowadays requires high performance computing, and therefore performance evaluation becomes a very significant task in such softwares. So performance evaluation on regular basis is an important task here. And why it is important? Because it can contribute to better scientific results, and it saves money. It saves money and energy, of course, by determining the bottlenecks. But the challenge is tracking performance on regular basis for such software on clusters or supercomputers, for example. And when you have many developers and huge parameter space, which is the case in most of the CFD softwares, then tasks become more tedious. Which brings me to our goal, where we develop an automated and systematic continuous benchmarking pipeline for waLBerla, which runs on different hardware architecture. But that is not enough. If we are running this, user would like to have a good feedback, a real-time feedback, and the best way would be visualization. So we have an automated and systematic pipeline for our framework with a visualization in an easy and accessible manner. So this whole pipeline is applied to waLBerla, and we will quickly see what waLBerla is. It is a highly parallelized C++-based simulation framework which performs computational fluid dynamics simulation. It is based on Lattice-Boltzmann method, but it also supports like particle fluid coupling and free surface flows. In today's presentation, I have taken an example of uniform grid CPU, which is basically pure Lattice-Boltzmann method performed on uniform grid. And we have taken different collision operators because for now you can just remember that different collision operators highly influence the performance of the code. Coming back to the pipeline, so this is the overview of the pipeline, and we will go through each component of the pipeline and see how it happens. Starting from when the developers commit and push changes to the source code repository. Source code repository here is our waLBerla GitLab repository, which is an open source repository. We want to run that on our test cluster. We will see in a minute what it is. So this source code repository already has access to continuous integration features of GitLab. And for running it on HPC resources, we need a custom GitLab runner. This custom GitLab runner is provided by NHR at FAU. And to access this HPC resources, we have a proxy repository. Now what this proxy repository does, whenever a developer commit and push changes to the waLBerla repository, this proxy repository basically pulls that code automatically, pipeline automatically get triggered, and proxy repository pulls that code and compiles and run the test on the test cluster. What is test cluster? Test cluster is a special HPC resource provided by NHR, where each compute node has different hardware architecture. So here in this pipeline, we only have single node benchmark because each node has different hardware architecture, but waLBerla is able to perform on multiple nodes as well. So now once you have the job running on the test cluster, you have benchmarks running on the test cluster, the next step is get the data. Here, the matrix we are considering is million lattice updates per second, which is a relevant matrix for Lattice-Boltzmann method. For CPU, we are using Liquid toolsuit. For GPU, we are using NVIDIA Insight Compute. And we are also gathering other matrices. So once the data is gathered, we parse it and we upload it to a database called InfluxDB. InfluxDB is an open source time series based database. why we chose InfluxDB and not any other database, because it is it is an optimized database for saving data based on time. It basically works like fields and tags. Fields are our main data, which is matrix, like it can be flops, time to solution, etc. And tags are our metadata. So in our case, it's domain size, it's number of processes, different architectures, etc. So once the pipeline is triggered and the jobs are run, each commit in the pipeline is saved as a single timestamp. So each data point is one commit. Once you have stored the database, once you have stored the matrix in the database, next thing is visualization. We use Grafana for visualization, and it again gives a real-time insight, and we will see in a minute how it looks. So once you have everything, this is how Grafana looks. And if I just click on Uniform Grid CPU, which is one of the benchmark, it looks like this. You see, these two matrices are the examples over here, and these are basically called panels. And we have different filters over here. So you can actually compare the performance changing different filters. For example, we have taken here different collision operators. So let's choose one of the collision operators. Yeah, let's choose one of the collision operators, and it's SRT. Here you can have different matrices. For example, I have runtime and M loops per process. You can select different hosts. You can select the branch, and most importantly, the time range. Once you select the time range, you will have your performance, which goes into the history and basically tells you how was your performance for each commit. You can also actually create your own query and group the data and visualize it in this. And you can also create dynamic plots with time as in x-axis. So here I am getting a closer look. You can just do it by dragging over the panel. And you see here red dots. Those are basically the commits. So you can go to the GitLab in the history and see what changes you made. So you can see using this, we can have a good feedback, and we can utilize the continuous benchmarking pipeline for knowing that how is the performance after changing the code. We not only have results for these matrices, but we also want to know that how our code is utilizing the hardware. So we have roofline model here, and which we can visualize in Grafana, where we basically use liquid bench for measuring different bandwidth benchmark, and we have a relative performance over here, which is approximately 80%. But for the host is architecture, so for that particular architecture with different collision operators. So you can change the architecture and of course the bandwidth and see how the code is performing. So this was all about the pipeline. Now future work is actually we want to extend it to multiple nodes, because waLBerla is built for running on multiple nodes. And for that, we want to use our own software, which is waLBerla, of course. And we are using our timing pool feature, and we are just implementing these matrices and want to get those matrices further. So this is an ongoing work, and I will just present it. Okay, it's not working. Oh, yeah, so we performed, for Uniform Grid CPU, we performed a weak scaling on Fritz supercomputer, which is Fritz cluster, which is CPU cluster, and each node has 72 cores. So we did up to 64 nodes, and we see that it has a perfect weak scaling, and we also plot parallel efficiency, and it's approximately 90%, which is expected because it uses communication hiding. So we do not we do not spend much time in communication. However, we have to justify it. So this is the communication lattice, load balance efficiency. And we see that, basically communication efficiency is the maximum useful computation time across all processor divided by the total runtime, and load balance efficiency is the average ratio of average useful computation time by maximum useful computation time across all processes. So we just implemented in waLBerla, and we see that communication is not the problem as expected. But if we go further, and if we run our code on multiple nodes, the load balancing could be a problem, and we have to improve it. So this is the ongoing work, and main thing is, yeah, we want to integrate this to our pipeline. So this brings me to my conclusion that we provide a continuous benchmarking pipeline, which is automated and structured for gathering the data and runs on different hardware architecture. And it provides real-time insights with good visualization. Most important future work is integrating the performance, which I just showed in the pipeline, and extending pipeline to the multiple nodes. Thank you, and I'm open for the question.